Okay, we're going to review for MVT, mean value theorem, Rolle's theorem, and also function first and second derivatives. All right, there are several things that you need to know. First derivative tells where the original function, is increasing or decreasing. Second derivative tells where the original function is concave up or concave down. If the first derivative is positive, that means if you're looking at your derivative graph, all your points lie above the x-axis would be where the derivative is positive, and if your points or the graph lies below the x-axis, that means your first derivative is negative. So if your first derivative is positive, the function is increasing. If the first derivative is negative, then the function is decreasing. Also, the second derivative is if the second derivative is positive, then the original function is concave up. If the second derivative is negative, then the function is concave down. So in this example, I have 4 of them. We're going to look for the original function. We're going to be able to tell which one is the original function and which one is the derivative, first derivative or second derivative. Okay, so I want to look at my black line to see if I can see if that's my function. So if I'm looking at my black line here, all right, so if I'm looking at this function, that would mean that I'm decreasing all the way down till I get to a point. So I'm decreasing all the way down to here. So that means that my function, if I'm decreasing, that means my original function, if I'm decreasing here, that means that my derivative needs to be below the x-axis. And it kind of looks like the red is below, but right in here, the red goes above the x-axis, so this can't be correct. So let's look at the blue graph. Okay, so the blue graph is decreasing from here all the way to here. So if I'm decreasing, that means my first derivative graph needs to be below the x-axis. Well, when I'm looking at let's see if I'm looking at the black, I am down here, but a little bit on that side. When I first start tracing a line, I'm a little here. That's a little above the x-axis, so that would be that the first derivative is increasing. And then we're supposed to be decreasing, so I'm supposed to be below all the way down till we get to about right here. And then my blue graph starts to increase all the way to get here, so that means the black graph should be above the x-axis until I get to about here. And then my function starts, I'm looking at the blue line for my function, the function starts to decrease, that means it decreases all the way here. That means my black line should be staying below the x-axis, but it goes here. So it doesn't seem like the blue graph is the function. I'm going to look at the red graph. All right, so if I'm increasing here, then I should be above the x-axis, and I see that the blue one is above the x-axis. If I decrease here and go to right here, that means that my blue graph would be below the x-axis. If I start to increase all the way up till I get to here, that means that from here, my blue graph stays above the x-axis until I get to here. And if I start to decrease here, then my blue graph stays below the x-axis. So that means that the red graph would be the function. So this is my function here. And the blue graph would be my derivative. So this would be f prime of x. And then my black graph has to be the second derivative. And we can actually check that because if I'm looking at my blue graph, so I'm looking at my blue graph here. This is, if I can see where my blue graph is increasing or decreasing, my derivative graph. So if my derivative graph is decreasing, then my black graph should be below the x-axis here. And then my derivative curve starts to increase here, then my black graph would be above the x-axis into here, and then the blue one starts to decrease here all the way down to this point somewhere right in here. Then my black graph is going to be below the x-axis, and then all of a sudden starts to increase, and then my black graph would be above the x-axis. So that's another way I could look at it as well. All right, and another way, if I'm looking at my derivative curves, my slopes of this curve right here are decreasing. So that means that my second derivative is negative, and I should have should be kind of concave. Let me see. If my slopes are decreasing. I don't like this. On which curve? The blue curve. Slopes are decreasing, and they start to increase. It means they're negative and they start to increase, so that means I'm going to be concave up. And then right here, they're negative and then they start to increase, so I'm going to be concave. I should be concave down. I should have been concave up, then concave down. And then I'm going to be concave up here. Yeah, that's another way of looking at it. Hopefully I didn't confuse you. Okay, let's see. Alright, so the next graph. Let's see if I can figure out which one is the function. Okay, so I want you to guess which one is the function, which one's the first derivative, which one is the second derivative. So pause the video for a second to see if you can figure that out before I reveal the answers. Alright, so the black graph is the function. The red graph is the first derivative. And the blue graph is the second derivative. Okay? That's what we have so far. Alright, so let's try the next one. So again, try to figure it out and pause the graph before I reveal the answers. Okay, so from this function, the red graph is the function. The black graph is the first derivative, and the blue graph is the second derivative. Alright, let's do the last one. Again, pause the video, try to figure out which one before I reveal the answers. Alright, so the function graph is the blue, so that's f of x. The red graph is the first derivative graph. And the, not blue. And the black graph is the second derivative. Alright. So if you got all of them correct, you should be okay for the exam on Tuesday. Alright, let's talk about the mean value theorem. Alright, so the formal statement of the mean value theorem states if a function f is continuous on a closed interval a to b and differentiable on the open interval a to b, then there exists a number c in the open interval a to b such that the derivative at c is equal to f of b minus f of a over b minus a. So remember, I keep saying that f prime of c is called the instantaneous rate of change. And f of b minus f of a over b minus a is called the average rate of change. So you need to make sure you know this terminology, because the problem on the test may be, or may say, find the average rate of change. You need to know that the average rate of change would be the slope between A and B. Okay? All right. So the translation states, if a function is continuous and differentiable, these are the key words to apply the mean value theorem. You cannot just look over these words. You got to read the problem carefully. It says, if function is continuous, that means there are no breaks, jumps, holds, sharp turns. I mean, not sharp turns, but no break, jumps, holes in the graph. All right, and differentiable. Differentiable means I can take the derivative. So there are no sharp corners or cusp or some type of discontinuity like vertical asymptotes. All right, it's differentiable if it doesn't have any sharp turns, any cusps, any vertical asymptotes, any vertical tangent lines, then that function is differentiable. All right, if it's differentiable, then it's continuous. Now, the vice versa method doesn't work for this, meaning that if it's continuous, then it's differentiable. That's not true. Okay, so again, if a function is differentiable, then it's continuous. But what's not true is the statement, if the function is continuous, then it's differentiable. All right. An example would be this. If I had the absolute value graph here, this function is not differentiable at x equals 0 because there's a sharp corner here. All right, or we call it a sharp turn, or we can even call it a cusp. That means it's sharp and then it takes off in a different direction. So this function would be continuous but not differentiable. All right, so that's an example of that. But make sure you read those questions on Tuesday's exam, because if you can miss that all of a sudden, so you need to make sure you're looking for continuity in the problem, and also that you're looking for differentiability in the problem. Because if you don't see that, then you can't apply the mean value theorem. If a function is continuous and differentiable, somewhere in the interval, the tangent line, which is the same thing as the instantaneous rate of change, must be parallel to the secant line. The secant line is the average rate of change. So again, the secant line is the average rate of change. This is the average rate of change. And the tangent line is the instantaneous rate of change, or it means the derivative at whatever x value that is. So the derivative in this case is the derivative at c. All right, so the instantaneous rate of change is equal to the average rate of change. Okay, that's what the mean value theorem guarantees. If the function is continuous on a closed interval and differentiable on an open interval, there is a c. There is at least one c. Okay, in the open interval a to b, such that the instantaneous rate of change, or tangent at c, is equal to the average rate of change, or the slope of the secant line. All means the same thing. And this is a picture of it. Okay. All right. Let's move to Rolle's theorem. Rolle's theorem is just a special case of the MVT. The formal statement says, if a function f is continuous and differentiable, has to be continuous and differentiable, and f of a is equal to f of b. So when you find the value of f of a, when you find the function value of f of a and that function value, which is f of b, at b, then there exists a number c in the open interval, so somewhere between a and b, such that the derivative at c is equal to 0. And you see, when we talk about derivatives, we're talking about slopes. So the slope at point C is a horizontal slope, which means the slope of a horizontal line is 0. Okay? So if a function is continuous and differentiable, the function must have a place with a horizontal tangent if there are two places where the function takes on the same value. All right, so again, if a function is continuous and differentiable, the function must have a place with a horizontal tangent if there are two places where the function takes on the same value, meaning that a and b have the same y value. In other words, there must be a relative minimum or maximum between the two places where the function takes on the same value. So in this case, this would be a relative maximum. All right. All right, so I have this example, and I want to know if I can apply Rolle's theorem or the mean value theorem to this problem. And if I can, if I can't, tell me why. I want you to pause the video and see if you can figure it out before I reveal the answer. Well, the first thing I would look at to see if the function is continuous, and the function is continuous. Remember, for a function to be continuous, there are three things that must happen. Okay, so the limit must exist. Remember the limit on the left side of C. So as the function is moving to the right here, this function is trying to get to f of c, and it does make it. All right, looking at the right side, as you're approaching c from the right side, the function is trying to get to the height of f of c, and it does make it. All right, so I know that the limit from the left and the right is exists. So the second thing is that f of c must exist. So the value of c must exist. So f of c does exist at this point here. All right, and I know that the limit of the function as x approaches c has to be equal to f of c, and they will have the same y value. So the function is definitely continuous. All right, so now look to see if the function is differentiable. Well, from looking at the graph, the function is not differentiable here because there's a cusp, what we call a cusp there. Or you can say it's a sharp turn, but for this part it would be called a cusp. All right, so that means that that function is not differentiable at x equals c. So that means that I cannot apply the MVT nor Rolle's theorem for this problem. Okay, let's look at another example. All right, can the mean value theorem or Rolle's theorem be applied? Why? All right, so again, I am going to pause the video. Well, I want to know if the function is continuous. Well, as I'm approaching b from the left, I'm at a different height as I would if I approach b from the right. My heights are different. Remember, for continuity to exist, the limits must be the same, and I have different limits. So my function is not continuous. Is not continuous. Because of that, we call that a jump discontinuity, because it has a jump discontinuity. All right, now I need to see if my function is differentiable. Well, remember, for differentiability, your function cannot have sharp turns, cusps, or any type of discontinuity. And we already said that we had a jump discontinuity, so that means that function is not differentiable at x equals b. So that means that I cannot apply mean value theorem or Rolle's theorem. All right, so this is an example that I'm going to use the MVT for to see if I can apply the MVT. All right, first I want to know if my function is continuous between -1 and 2. So I'm looking at my function. It's a cubic function, and this is a polynomial, so I know that all polynomials are continuous functions, okay? You should have some experience with doing polynomials in the previous math classes. All polynomials are, and I'm going to write this down, all polynomials are continuous. And that's a true statement, are continuous. All right, so the first thing I'm going to, and I want to know if it's differentiability. It is differentiable. I can take the derivative of every point within that interval, okay? So I'm going to actually take the derivative of the function now. F prime of x is equal to 3x squared plus 4x minus 1. So that's my derivative function. And then I'm going to find the average rate of change, which is the slope of the secant line. So I need to find my y values for -1 and my y value for 2, f of 2. So I have -1 cubed plus 2 times -1 squared minus -1. So it's going to give me -1 plus 2 plus 1, which is going to give me 2. So I have a point -1, 2. And then I'm going to find my other y value, which is going to be 2 cubed plus 2 times 2 squared minus 2. So I get 8 plus 2 squared is 4 times 2 is 8 minus 2 is going to give me 16 minus 2, which is 14. So my other point is going to be 214. I'm going to find the average rate of change. So I'm going to use my slope formula. You normally you say f of 2 minus f of -1 over 2 minus a -1. It's the same thing as saying y sub 2 minus y sub 1 over x sub 2 y sub 2. Okay, 14 minus 2. So it'll be 14 minus 2 over 2 minus a -1. So it'll be 14 minus 2, which is 12, over 2 plus 1, which is 3, and that gives me 4. So my average rate of change is 4. So what you want to do is set the average rate of change equal to the instantaneous rate of change to solve for that value that lies between -1 and 2. It could be 2 values, but you want to find at least one value. So if I take 3x squared plus 4x minus 1 and set it equal to 4, it's a quadratic equation, so I can subtract 4 over. With quadratics, you want one side to be 0. So it'll give me 3x squared plus 4x minus 5 is equal to 0. Now, I found the average rate of change and I found the derivative at a point. So what I'm doing is I'm trying to find that c that lies between -1 and 2. Now, if the directions if the direction do not tell you to find that c, then you don't need to do this part that I just blocked. All right, but if it tells you to find that c, then you need to do this part here, what I'm working on now. So I have 3x squared plus 4x minus 5. So I'm going to use the quadratic equation, which one would be easier than factoring. So I have a is equal to 3, b is equal to 4, and c is equal to -5. So I have x equals -b plus or minus square root of b squared minus 4ac all over 2a. So I'm going to have a -4 plus, I'm going to square that 4, and I'm going to get 16 minus 4 times 3 times a -5 all over 2 times 3. So I'm getting -4 plus or minus, this is going to be 16. That's a -12 times a -5 is a +60. Yeah. All over 6. All right. So I'm going to get -4 plus or minus the square root of 76 all over 6. All right, so that is my x values. I need to actually see if I can expand the square root of 76. Let me see what that's going to be. Hold on a second. All right, so we can break that radical 76 into square root of 4 times 19 over 6, but then that could be negative 4 plus or minus 2 radical 19 over 6, and then I just need to reduce negative 4 divided by 6 is going to give me, reducing that by 2, that's 2. Yeah, I can reduce this, everything by 2. So it'll be negative 4 divided by 2 is negative 2. 2 divided by 2 is 1. And then I'll have radical 19 over here and reduce the 6 by 2. I get 3. So I get negative 2 plus or minus radical 19 over 3. That's equal to x. So I have two values of x. I'm going to go to the next page to make sure that I'm getting a value between those two. So it'll be negative 2. So it'll be negative 2. Okay, I think I got this thing right. So it would be x equals negative 2 plus or minus radical 19 over 3. I think that's what it was. Negative 2 plus or minus radical 19 over 3. All right, so at this point, I can actually use a calculator to actually calculate this. I'll have negative 2 plus radical 19 over 3. And then I'll have x is equal to negative 2 minus radical 19 over 3. Okay, just need to get my x values to see if those values are between my interval, which is negative 1 to 2. Okay, so let me get a calculator. Let me calculate this. All right, so when I used the calculator, I got 0.786 for negative 2 plus the square root of 19 divided by 3. And I got negative 2.20 for the negative 2 minus radical 19 over 3. So the one that is between negative 1 and 2 would have to be 0.786. All right, so if I drew a number line, if you can't see that, if I drew a number line, this is negative 1, 0, 1, 2, and that's 0.786. So that's close to 1. So that means that my answer is 0.786. So that C value would be 0.786 that exists between A and B, which would be negative 1 and 2. All right. All right. This is an example of Rolle's theorem. All right. So according to Rolle's theorem, let's go back to Rolle's theorem. The function has to be continuous on a closed interval and differentiable on an open interval. And f of A and f of B, the y values for A and B, must be equal to each other. Then you can apply Rolle's theorem that states there exists a C in the open interval AB such that the derivative at C is equal to 0. So if A and B have the same y values, and if you drew a line from one point to the other point, that should be a horizontal line. And if that line is horizontal, then f of prime at whatever value that lies between A and B also has a slope of 0, which is another horizontal line that's parallel to the horizontal line that exists between f of A and B, f of B. So let's just do an example. Hopefully you can understand it through the example. All right, so the first thing I'm going to do is find f of negative 1, which I put negative 1 in to the equation. So it'll be negative 1 squared times negative 2 minus 2 times negative 1 plus 1. So I get 1. And negative 2 times negative 1 is a positive 2. Plus 1 will give me 2, 3, 4. All right, then f of 3. F of 3. All right, so if I plug in 3, I get 3 squared minus 2 times 3 plus 1 is equal to 3 times 3 is 9 minus 2 times 3 is 6 plus 1. 9 minus 6 is 3 plus 1 is equal to 4. So my points are -1, 4 and 3, 4. All right, and I see that the y values are the same. All right, and there's a horizontal line between -1, 4 and 3, 4. All right, and I can kind of draw the function. Let me see if I can actually bring the function in. All right, so now we have the graph. So we have at point -1, 4 and 3, 4, there's a horizontal line between. If we draw a horizontal line, then Rolle's theorem says that there exists a C that's between some C that's between -1, 3, such that f of prime of C is equal to 0. So you know the slope of a horizontal line is 0. So again, Rolle's theorem says that there is a C that's between -1 and 3, in which the derivative at C is equal to 0. All right, so we found our 2 points. We drew a horizontal line. Then we're going to find the derivative of the function, and it's going to be 2x minus 2. And we're going to set that derivative equal to 0. So I have 2x minus 2 is equal to 0. If I add 2, I get 2x is equal to 2 divided by 2, x is equal to 1. So I see that 1 is between 1, x equals 1 is between -3 and, -1 and 3. All right, so right here, if I take the derivative of the graph at this point, that means I'm looking for the slope at that point, then my slope is equal to 0. All right, so the function's continuous and differentiable. You're going to find the y values of your interval values, and then you're going to draw a horizontal line through those y values and look at, since it's a horizontal line, that means the slope is going to be 0. Then you're going to take the derivative of the function, set the derivative equal to 0, and then solve that, and you get x is equal to 1. So at x equals 1, the derivative of that function is 0. And that's pretty much it. So if you know all this information, you can kind of go through it and understand the process. Make sure you read the questions well so that you'll know what you're being asked to do. Then you should be good for this exam. I'm sorry the video took 32 minutes, but I want to make sure that I explain all points, all things in the on the test that you will see. So anyway, good luck on the exam on Tuesday.